Welcome, everybody. Today we have Robert, Dougherty-Bliss? Dougherty-Bliss. I should have confirmed that before I got up here. Sorry.
Don't worry about it.
Anyway, he will be telling us about the ergonomics of computer algebra.
Okay, thank you, Yona. I appreciate the introduction. I should also, I guess, say thank you to Dr. Z for very politely telling me that I was going to be speaking here today. Very gracious welcome to Rutgers. So today we're going to talk a little bit about computer algebra. This is going to be, I think, a slightly different talk than what we're used to in the experimental math seminar, because we're not going to be talking about math results so much. We're going to be talking about what makes experimental techniques so unique, and that's the tools that we use to get those results. So if you get anything out of this talk today, it's that tools are very important and that you should care about them. Results are also important, but how you get them can be just as crucial to your work and to your life and well-being. So you can leave now if that's all you want to get out of it, but maybe don't. So I'm used to giving this talk. The tool we're going to focus on is computer algebra, and I'm used to giving this talk to undergrads who study things like English or philosophy. So I have to show them this to remind them like what algebra is first. So I show them something like this, and they usually look something like that. They kind of like, they furrow their brow and they go, algebra, yes, I remember this from sometime in my life. And then maybe if I like really want to make them squirm, I like ask them to solve that or something. But anyway, so then to remind them what computers are, I show them something like this, which is in principle the same thing, it's just a lot scarier, right? I mean, not scarier for a computer, for someone who knows how Gaussian elimination works, but they study philosophy, so what do they know? Then they usually look like that. And then I get them on my side, and I say, don't worry, don't worry, don't worry. You don't have to do any math. The computer will do it all for you. So I don't think I need to convince anyone here that computer algebra is important, so I'll just hope that you're with me and don't ask any questions if you don't like computer algebra. Cool. So the big picture here today is, like I said, we're going to talk about tools. So there are some tools that we made once and we got right, and we don't need to touch anymore. Things like hammers, or simple machines like a ramp, or like a lever, pulleys. Those are good. You don't need to touch those. Some things are not so good, and those are things like computer algebra systems. So computer algebra systems we made once and we definitely screwed it up, and we need to fix it and keep making them until we get them better, right? So we should try and find, of the computer algebra systems we have, think of them as tools and find ways to evaluate them as such, and try and find the best computer algebra system that we can use to make our work go a little bit smoother. Make sense? Cool, very polite nods. So when I say the best computer algebra system, I do want to clarify one thing. I don't mean the fastest computer algebra system, and I don't mean the one that can do the fanciest stuff. I don't mean the one with the most algorithms, or that has like the best mathematicians working on it, or has a bunch of money put into it, blah, 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 things like that. I'm specifically talking about the ergonomics of the computer algebra system. So have you guys heard of the term ergonomics before? Maybe you've heard like ergonomical keyboards, like that have weird shapes for your hands, or like special chairs that support your back in like a certain way. So that's one kind of ergonomics that focuses on physical comfort. But ergonomics is a general field that studies lots of things, like mental strain and things like that. So if you want an example, one part of ergonomics you could think of is like the environment that you work in your workplace. So Hill doesn't have very much natural lighting in our offices, for instance. So it's got bad ergonomics. Don't tell anyone I said that. So one particular thing that people study in ergonomics is this thing called mental workload. So mental workload is roughly how hard you need to think when you're trying to solve a problem or do some task at your job. And this is kind of important. So you might think that you want to do work where you have to think very hard to get stuff done. But that's not true. That's bad. You want to not think when you're getting things done. That's like the whole point of like a computer algebra system. You just go, I want the answer, go find it for me. And I don't want to have to think too hard about it. Now, mental workload is not just some like silly thing that you can think of for like frail office workers to think about and make it seem like their jobs are hard. Mental workload is important. So there were some studies in aviation instance which suggested that as much as 18% of pilot errors are due to confusing instrument design. So that means that someone was trying to read an instrument in their cockpit, and they either couldn't understand it or couldn't understand it fast enough because it was designed poorly. It was designed in a confusing way. And that just goes to show that the tools that we design should be simple, convenient, and easy to use. And that extends all the way from planes to computer algebra systems. So what we're really going to talk about is that some computer algebra systems are more ergonomic than others. So here's a quick demonstration to show what I mean by ergonomics, just to make sure we're on the same page. So here are two functions which do exactly the same thing. They're in some made-up language that I made up like an hour ago. So they both take in two numbers and they return their sum. The first one takes in the two numbers and returns their sum. The second one takes the two numbers, adds them together over here, adds them together over here, adds 100 over here, subtracts 100 over here, checks if the two things are the same, and then returns it if they are. So they obviously do the same thing, and they even have the same asymptotic runtime complexity. They both run in like nearly constant time. But boy, that one on the top sure is nicer, isn't it? It's only one line. It's only got two variables in it. You don't need to think very hard to read it, even though they do functionally the exact same thing. So languages that help us and encourage us to write things like the first one are desirable, and things that encourage us to write things like the second one are bad, and you don't want those. Good enough? All right. So we want to find a way to measure these ergonomics of computer algebra systems, rather than just looking at things and making judgment calls about them. And how we're going to do that is we're going to borrow the idea of this computer scientist named Maurice Halstead. I think he was at Purdue back in the 70s. So he published this book in 77 called The Elements of Software Science. And in that book, he tries to outline a way that you can actually reason about programs, and not just computationally, but how you can reason about them ergonomically, how you can reason about them from a programmer's perspective. How hard is this language to use? How difficult is it to understand? Is this program complicated? Is it simple? What kinds of things can we learn about it just by reading it and making simple observations that you could automate with another computer? So what you do is you take a program written in some language and you measure some things about it, some simple things that I'll show you in just a second, and then you combine those measurements in a few different calculations and metrics that we now call the Halstead complexity metrics, or just the Halstead metrics for short. So let's see if we can talk a little bit about what they are. So the first four things you need to know about a program, I guess the first five things. The first thing is that you think of a program as a sequence of operators and operands. So it's a sequence of variable declarations, function calls, things like that, calculations that you do. And the measurables that we have here are eta1, eta2, big N1, and big N2. So eta1 is the number of distinct operators, eta2 is the number of distinct operands, and then N1 and N2 are just the total number, respectively. And you can get those just by reading a program. You can have some other program automate reading that and calculating these. It's not too hard to do as long as you have some convenient tools in your language of choice. Then once you take these measurables here, you combine them in these significantly more complicated metrics. So the first two are relatively straightforward. So program vocabulary is the number of unique things in your program. So it's the number of unique operators and operands. So it's like the total number of things that you need to know to read a program. Program length is just the total number of things in your program. So it's how many things you need to read to understand the program. And then these last four are a little more complicated, and maybe we should go through one at a time and explain what they are. So this first one here we call volume. So it is big N, which is the length of the program, times log base 2 of the vocabulary. So I guess the easiest way to understand that is it is the smallest number of bits that you need to represent your program in binary. So log base 2 of eta, there are eta unique things. Eta like total unique operators and operands. So log base 2 of eta, that's the number of bits you need to represent one of those things. and then their big N of those things total. So without using any fancy encoding scheme, you just need that many bits to write your program down, which is kind of a measure of how big your program is. Sort of a different measure from length. And then in Halstead's book, he has another kind of interesting interpretation of this, which is a little dubious, but I think it's fun, so we should talk about it. So imagine that when you're writing your program, you decide that you need to put in a certain operator and operand. And to pick which one you need, your brain does a search in your head for which one it wants. And let's pretend that it does a binary search, because that makes sense, right? Binary searches are pretty good. So pretend that your list of operators and operands are in like some sort of array, and you do a binary search to find the one that you want. Well, a binary search means log base 2 of eta, on average, comparisons to find the thing that you need. And then you have big N things that you need to look up. So you need volume mental comparisons or discriminations to write your program code. So anyway. So the next two metrics, L is level, program level, and D is difficulty. So this is supposed to be kind of a way to quantify how high level or low level your program is. So high level in the sense of like you're trying to abstract away details and not worrying so much about like concrete calculations and more just thinking about ideas. If you know any programming languages, think of, say, the difference between like maybe a Lisp implementation and C or assembly language, something like that, a high-level language versus a low-level language. And the rough idea behind this metric is it's kind of like a joint measurement between two different things. So that first factor there, eta 1, measures one thing, and then the second factor here measures a different thing, and when you multiply them together, you get a full metric. And the rough idea here is that the language level is small if there are few, often repeated variables and many different operators. So that would be lower level, and the opposite would be higher level. And then difficulty is 1 over L, because a lower level language means you have to keep track of more things in your head as you go. So that's Halstead's reasoning there. Effort is just you multiply difficulty times volume, and that's sort of like a program is this big, and you had to work this hard, so here's a measurement of the total amount of work that you had to do. But maybe don't worry about the units, because that would be an inch. Anyway, so one thing is that the Halstead metrics kind of sound like I just made them up, and so why should you believe anything that I said about them? So we can give a little bit of credence to the idea that they mean something, that you can measure things about a program, like simple facts, and then predict things about it. And here's another metric that I didn't introduce. It's called computed length. So it looks kind of like entropy, if you've ever seen that before, but don't worry too much about it. It's just like you take your eta variables and you plug them into this formula, and this is supposed to give you an estimate of how long your program is. And you might think, well, this is just completely made up. Why would this mean anything at all about our actual program? But it does mean something, and here are some graphs to prove that. So this is a graph of program length versus computed program length, except I wrote expected there. So what I've done here is I've taken a bunch of functions from a Python library called requests. So it's a very popular Python library that does like web-based stuff. It's not too important what it does. It's just important that when this library was written, nobody was thinking about the Halstead metrics at all. I had nothing to do with it. But if you look here, program length and computed program length are very nicely correlated linearly. They're like almost unreasonably nicely correlated. It's like you can have this nice estimate for how long your program actually should be just based on these like fake eta variables that we just came up with. So there's some correlation there between the two.
When you have actual program length, is that measured in like lines of code?
Actual program length is the sum of the number of operators and number of operands. So not how many lines, but like how many individual things. So maybe a good point. Program length in terms of lines could be artificially inflated, and it might not actually represent how much you have to understand to read it. So here's a second picture using a different Python library called Django, which is another web thing. And this is slightly less linear, but still like unreasonably linear, I think, to show that somehow this weird entropy-like calculation can tell you how long your program should be based on how many unique things that you use. So Halstead was onto something. Definitely he's onto something here. I think these graphs lend some credence to his work. But let's get back to computer algebra. So the whole point of what we're going to do here is we're going to take two different computer algebra systems and we're going to solve the same problem using two different systems. So I used Python with their SymPy library, which is a symbolic library, which does computer algebra, and then I used Maple. And we're going to look at three different problems and solve them in both, and then we're going to compute the Halstead metrics for the two solutions, and we're going to see what they look like at the end, which one had better scores. And then maybe, using that, we can try and figure out which one is a little bit better or simpler to use. Does everyone make sense? On board? Cool. So, I'll spare you all the confusing details and just show you the pretty pictures. So, what we're looking at here is a histogram of the logarithm of the effort metric, the effort Halstead metric. So, I've taken the SymPy code that implements a few different summation algorithms, like Gosper's algorithm, Zahlberger's algorithm, a few other things, and the corresponding Maple code that does that, and I've computed the Halstead metrics for every function in those different packages, and then I took effort, I took the logarithm, because effort's kind of big, and then I threw them all into a histogram. So what you can see here is that the bulk of the blue histogram, the Python one, is slightly to the left of the red histogram, which means that, on average, the Python programs had lower required effort. Not always, there's some red over there for Maple stuff, but the bulk of the red is over there. And actually, because this is the logarithm of effort, this is something like, this line right there isn't just 12, it's actually 10 to the 12. And that line right there isn't 6, it's 10 to the 6th. So that's actually a pretty pronounced difference between the two. Anyone have any questions about this histogram? Because there's going to be two more of these. So if you're confused in the first one, you're going to be confused for two more slides. Cool. All right, your fault. All right, so this next one is Boolean satisfiability. So this is maybe a little more complicated. Think of it as I give you like a Boolean expression, something with variables in it, and I've got some logical connectives like and, or, not, stuff like that. And you just tell me if there's a way to make that sentence true by assigning the variables different values. And that's a problem called Boolean satisfiability, very important problem in complexity theory, and we don't care about it right now. We only care about this graph. So both Python and Maple, or SymPy and Maple, both have procedures to solve this problem in various different ways. Python has quite a few more, so there's more data available. But we've computed the same histogram as on the last slide, and this time, though a big bulk of the blue histogram is further to the left, Maple does have a nice big spike here, lower, but there's still this big chunk over here, which is further to the right. So it's not as clear of a conclusion as on the last slide, but there's still something to be said. Like the bulk of the blue histogram is still a little bit further to the left than the bulk of the red histogram. This last one here is a problem that's probably not that well known. I call it the Pisot problem. This problem comes from, Neil Sloan's not here today, but a problem that Neil Sloan and Dr. Z worked on, actually, about these things called Pisot sequences, which I guess I won't get into too much detail, but the gist of it is you have some very complicated recurrence. You have some sequence that satisfies a very complicated recurrence, and sometimes they satisfy nice recurrences. And the question is, what are those nice recurrences, and when do they satisfy them? And it turns out you can answer that question with some fancy computer algebra using polynomial stuff. And Dr. Z and Neil Sloan wrote some Maple packages to solve that problem, and now there are some Python packages. And if you care about the actual problem itself, you can just Google the name of their paper, and I think you can find it on Dr. Z's webpage. But here, again, comparing the Maple and Python solutions, the bulk of the blue histogram is to the left of the bulk of the red histogram. So on average, the Python solutions had lower required effort than the Maple solutions. So that's certainly 2 times we've seen that conclusion, and then the second time was maybe a little more iffy. It's definitely not a foolproof conclusion. But, so now that we've seen sort of quantitatively that Maple might have sort of higher effort scores in trying to solve the same problems with computer algebra techniques, it might be worthwhile to try and understand why that is. You know, it's one thing to just look at the numbers, it's maybe a little bit harder to figure out why they're occurring the way that they are. And I think a good reason that Maple might be scoring higher in effort is that Maple is really designed first and foremost as a computer algebra system. And it does a lot of other fancy stuff. It does computer algebra. You can design apps with it. You can teach students calculus and linear algebra. You can run physics and engineering simulations. And with all that fancy stuff, it also has to be a programming language at the same time. And that programming language, I think, is kind of an afterthought in the design. And there's some good evidence for that. So Maple was released in 1982, I think, which is pretty old as far as programming languages go. Is that almost 40 years now? Nearly 40 years? So Maple was released in 82, and then 30 years later they decided, maybe we should implement classes. Maybe object-oriented programming is like the hip new thing. Except that has been the hip new thing for like 20 years at that point. So they're really lagging behind the language design department. They're very good at computer algebra, they're great at that, and they're great at the simulations and everything else, all the fancy stuff they do with their nice interface, or with their interface. But as far as like programming language design, they haven't really focused on that too much. And some of the things that we've seen from newer languages to explicitly make, other languages explicitly make their design goals clear, like we want a simple language that's nice to use and not complicated. And Maple went, let's just throw everything we can, all at once. Like if you see from this is from an official Maple release. So Maple is both a procedural language, an object-oriented language, and a functional language, all at once. So it just tries to do a bunch of stuff, and maybe not all of it very well. Anyway, so other languages, I guess, because I've been talking about Python, I'll specifically mention it. Other languages, very, very much at the forefront of their design philosophy is simplicity and trying to make the languages nice to use for beginners and experts alike. So here's a nice quote from the creator of Python. I won't read it, you can read it. It's just about how there was this overriding spirit in the design process to try and find a way to make the language simple and higher level so the abstractions are useful in the design of your programs. And I think while Maple is very, very good at what it does, it's very a specialized tool at computer algebra, it's not so good at the ergonomic part. It's not so good at being a comfortable tool that's nice to use. If you think about, say, like a hammer, imagine if you took a hammer and you put a laser sight on it. And then you could very accurately aim your hammer, right? Like you would never miss. But what if the grip of the hammer was made of brick or something like that? It'd be great that you could never miss this thing, but you would want to stop swinging after 2 swings because it wouldn't be comfortable. So I think you would much rather have a nice hammer with a comfortable grip that maybe you hit your thumb every now and then. But, it's easier to use after 100 swings or something like that. So I think that if there are any programmers in the room, I'm not sure who's done how much programming, there's definitely sort of this gut feeling that some languages are simpler than other languages for solving the same problem. And the Halstead metrics give us a way to actually talk about that and a way to quantify how some languages are simpler than others. So I don't think the conclusions here are all that surprising, that it's at least possible to do this. It might be possible to do it in a better way. The Halstead metrics are, also nearly 40 years old, or maybe a little more than 40 years old now. But it's something that we should be familiar with as people who use a bunch of different programming languages. Like I said in the beginning, languages are not timeless tools. Programming languages are fairly recent inventions, and we're still iterating on what the best ones are and what the good design ideas are. But it's definitely clear that computer algebra and programming in general is becoming more and more important in research in all kinds of different fields. And I think especially in math, with the design of really great computer algebra systems. And as they become more and more important and more useful, we should probably notice that we can make them better and make our work a lot easier to get done. Mathematicians don't seem to care too much about that, if you've ever read like some Maple code or anything that a mathematician has read, I'm sorry that you had to do that. But I think that they could be made to see that it's an important problem and that they should think a little bit more about it. Maybe they just need a little bit more prodding, or maybe they need some new people to just replace them. But we'll see how it goes. So I think that there's definitely something to be said for thinking a little bit more about the programming languages that we use, the environments that we create, and how ergonomic they are. So I'll stop there. Does anyone have any questions?
First, let's thank Robert. And then...
I was just thinking, like, if you give this talk in the computer science department or something, like, I think a lot of the people, like, there's one step in understanding of programming, in the understanding of program, which is like reading through and figuring out what all the operations are doing and sort of what the Halstead metrics are measuring. And then there's sort of another step, which is that proving that that algorithm does what you want it to do.
Yes.
And I think some languages are sort of more designed to like guide with that proof, maybe increasing the number of operations, but maybe it makes it like easier to see why it does something else.
No, that's true. I don't know if any languages are explicitly designed to make it easier to prove things, except for maybe Coke or something like that.
Yeah, or maybe just like the people writing the code don't optimize for the Halstead metrics for some reason.
No, you should not optimize for the Halstead metrics. That would be bad.
Okay, yeah, that's what I think.
No, but you're right. You're right. There are many different ways that you can think about the complexity of code. The Halstead metrics is one way that I for a while I called it the expressive complexity, which is it's not so much what is the algorithm doing, it's how hard do you need to work to understand it. And I mean, maybe there's something to be said that it would be easier to automate program correctness if your program was something that a computer could understand. But at the end of the day, I want to be able to understand it too. So I don't know. That's a good point.
Has someone come along and developed like specific guidelines for either for this sort of complexity or for some other sort of complexity that would complement the Halstead rules?
I don't know if anyone has written guidelines specifically referencing the Halstead metrics, if that was the question.
Or maybe a different set of metrics that would complement those and capture other forms of complexity.
So there are a couple different measurements of complexity. I think, I'm going to mess up the name. There's a few, I think it's called cyclomatic complexity, which if I remember is like how many different logical branches are there in your program. But at the end of the day, I don't know if anyone has written guidelines, though, to actually say, you should do this to minimize complexity, or you should do that, with reference to specific metrics. But lots of programming languages, and math people wouldn't know this, because they don't look for it, have these things called style guides, which do tell you, you should write things that look like this, because experience has shown it makes things easier to understand. But none of them actually reference specific complexity metrics, no. Which could be interesting to think about.
Do we have other questions? All right, let's thank Robert again.